All right, so next up, second problem. Now we want to go ahead and just solve the system of equations. Now, again, I know that this is one that we're specifically addressing, talking about in class today. But again, we want to be prepared for something like this, not caught off guard. Where we might fall victim is we might try to use the elimination method. Honestly, there is a way that we can do the elimination method. I just feel like this one is so much set up for the substitution problem. So if we were to recognize that x is actually equivalent to y plus 2, that tells us now exactly what we should put place for x. So remembering, just rewriting, we have x squared minus y is equal to 4, but we know that x is actually equivalent to y plus 2. So that tells us that we actually have to square the y plus 2, which, remember, we have to do the FOIL method in order to get that. So in FOILing out y plus 2 times y plus 2, again, first would be y squared, outside would be 2y, inside is also 2y, together that's 4y. Our last term, 2 times 2, would be 4, and we still have our minus y is equal to 4. So from here, in cleaning things up, I'm going to try to get everything over to the left side. I also am going to combine my like terms. 4y minus y is going to be 3y. And like I said, if I subtract this 4 over, now we're going to be equivalent to 0. So at this stage, again, factoring, I'm going to factor out a y, leaving me with y plus 3. And now we are where we want to be, in the sense that I can say that y is equal to 0. I can also say that y plus 3 is equal to 0, which tells me that y equals 3. So, again, at the very beginning of that problem, if we instead wanted to go a slightly different route, excuse me, and if I would have, I don't know, maybe rewritten this as I subtract the y over x minus y is equal to 2, and I still got my x squared minus y is equal to 4. So if you're questioning, could we have done the elimination method with the y's, you're absolutely right. Again, we could have multiplied through by a negative 1 on the top, so negative there, positive there, negative there. And again, not that we're going to do this entire problem, but think about what that would have given. We can't combine, so x squared minus x, the y's would have canceled, is equal to 2. And again, we could have absolutely targeted and gone from here. So, speaking of this problem, again, this would have been a different route, but we so far have only solved for the y's. So again, we have the answers that y is equal to 0, y is also equal to negative 3. But what does x equal? So for this particular problem, I think that it's going to be simplest for us to use that top equation, x is equal to y plus 2. So coming back down here, x is equal to y plus 2. As soon as we recognize that y is equal to 0 and sub that in, now I know that x is equal excuse me, to 2. And realizing, of course, that it's like a partnership. They go together. We know that if x is equal to 2, y is equal to 0. And those, again, go together. Next, if we were to utilize the y minus 3, if I were to put a negative 3 in place here, again, y is equal to negative 3 plus 2. Combining there, now I get that x is equal to negative 1. Again, the partnership, they go together. When x is equal to negative 1, y is equal to negative 3. Again, a lot of different ways that we could have gotten there. I think I showed through elimination we could have found the x's first, but when we did this problem, we found the y's first, and we went from there. All right, so jumping over to number 3, where we have the 3-variable system of equations. Again, a lot of different ways that we could approach these problems. Again, it's good to have choices, but I think that targeting and getting rid of the z's is probably going to be our best option. So I say that because we're already set up for an exact elimination, I suppose, just by combining rows 2 and 3. So if I were to combine row 2 and row 3 together, again, simple as could be, we're going to look at 4x plus 5x to get 9x. We'll look at 6y plus 3y to get 9y. We look at negative z, positive z, they cancel. Excuse me, we look at negative 4 plus 13. We also All right, so off to a great start. It's going to be a little bit more of a challenge, I suppose, to get to next, but hardly. It's just that we have to multiply the middle equation through. Again, we're still targeting the z's that we want to cancel, but I think that we're going to have to multiply through by a 3 because, again, we're trying to create a cancellation with positive 3z in row 1. We're trying to create a negative 3z now here in row 2. So by distributing that 3 through, that's going to give me 12x plus 18y minus 3z, running out of space here quickly, is equal to negative 12. And down here, the plan is that I want to take my first row plus, remember, we're doing 3 times the second row. So in doing exactly that, x plus 12x is going to give us 13x. Negative 2y plus 18y is going to give us 16y. The 3z and the negative 3z will cancel, and 19 plus negative 12 gives us positive 7. This is my new system of equations that we're going to go about solving. So the way we go about solving this system of equations, again, we could do this multiple ways. Usually I would say that we want to stay as far away from fractions as possible, but you might notice conveniently in that top row that we have coefficients of 9 all the way through. So I'm going to target the x's. I think that if I multiply through by negative 13 ninths, like I said, on the surface that seems like, what are you thinking? Why would you possibly do it that way? But the coefficient and the denominator, they're going to cancel in all cases. So when I distribute through 9x times negative 13 over 9, again, looking at something like this, 9x over 1 times negative 13 over 9, where these 9's cancel, that's just going to leave me with negative 13x. So in that top row, again, that's going to leave me now negative 13x minus 13y is equal to negative 13. If the bottom row stays the exact same, again, 13x plus 16y is equal to 7. Our elimination is set up where the x's cancel. Negative 13y plus 16y is positive 3y. Negative 13 plus 7 is going to be negative 6. Now I know that y is equivalent to negative 2. Going back into this secondary system, it again does not matter which of the equations we go with. Again, I suppose I'll go with the top to where we can say that 9x plus 9y is equal to 9. Right. And we just figured that y was equal to negative 2. So in calculating, again, now 9x minus 18 is equal to 9. Add the 18 over. 9x equals 27. And now we know that x is equal to 3. So if x is 3 and y is 2, now we need to go back to the original system, and we need to choose one of these 3 original equations. It doesn't matter which one. Again, honestly, couldn't care less which one we decide to use. I guess the top, I don't know. So the top, so we'll just copy this down. X minus 2y plus 3z is equal to 19. But right now we know that x is 3 minus 2 times y, which we know is negative 2, plus 3 times z is equal to 19. So cleaning this up, 3 plus 4 plus 3z is equal to 19. It's going to clean up here, combining like terms. 7 plus 3z equals 19. Subtract the 7 over, 3z is equal to 12. And finally, we know that z is equal to 4. So I don't know if I can get all of this on the same slide. In fact, I cannot. But if x is 3, y is negative 2, z is 4, remember the way that we would present that answer is as an ordered triple. 3, negative 2, positive 4, and we get it. All right, so next up, number 4, we're asked to sketch the solution set and label the vertices of the system. So this time the system was given to us. We have it right there in front of us, and we just want to sketch it, and then we need to address any shading that is necessary. So for this problem to be successful in this problem, I think that we need to get into a graphable form. So for the top equation, or inequality, excuse me, I'm going to add x squared to both sides. And I feel like that's going to give us y is greater than x squared plus 1. Okay, so I'll use red here for this one. If I were to look at y is greater than x squared plus 1, this is just the parent function shifted up 1 unit. I'm also noticing that this is a greater than, not greater than or equal to, which tells me that this is going to be a dotted line. So for your parabola, if you go right 1, you go up 1, left 1, you're up 1. Right 2, you're up 4, left 2, you're up 4. Right 3, you're up 9, left 3, you're up 9. And if you don't know those things, I'd be a little surprised, honestly, by now. But if you don't know those things, then you can create, literally create a T-chart, and you can go from there. So this is the start of my problem. Again, if we were to test 0, 0 for shading purposes, if I put a 0 in for y, greater than, if I put a 0 in place for x, 0 squared is still 0 plus 1, 1. Is that true? Is 0 greater than 1? And the answer is no. That's not true. So that means that I'm not going to shade this parabola in a way that it's going to cover the origin. So I'm not going to shade in the exterior, instead now the interior of that parabola. So again, something to just kind of keep in mind moving forward. For the side, I'm going to come down here and do this. We have negative x minus y greater than or equal to negative 3. Again, I'm trying to isolate the y. So if I were to add the x over, 3. Now I've got to divide everything by negative 1 to obtain positive y here, negative x here, negative 3 here. And when you divide by a negative, we have to flip the sign. So in that system, that graphable system, I'll write this one up in blue because that's how I plan to graph it. We'll say y is now less than or equal to negative x, not plus, but minus 3. So negative x minus 3. Again, this is the system that we're trying to create. So this is linear, just a line, that's all that we need. We started the y-axis at, you know what, I screwed up the sign, didn't I? I'm starting to, just luckily out of the corner of my eyes, I caught a little glimpse of my work. I had a negative 3 right here, and for some reason I changed it over to positive 3. So definitely don't want to do that, but that should be a positive 3. Sorry about that. Like I said, glad that I caught it before I actually drew the line. Okay, so that changes the fact that my y-intercept is up here at positive 3. I have a slope of negative 1, so I'm going to go down 1 over 1, or up 1 left 1. And I'm noticing again that this is less than or equal to, which means that this is going to be a solid line. In terms of that same testing of 0 in for x, 0 in for y, testing does the origin work? If I put a 0 in place for y, less than or equal to 0 in place for x, 3, we would say that yes, absolutely, 0 is less than or equal to 3, so in accordance to the blue line, I will shade toward the origin. Remembering also that in accordance to the parabola, we said we needed to shade in the interior, so we need to shade in the region that is in the interior of the parabola, but below the line. All right, so that's where we are at so far. Last problem that we have, again, we're not going to be able to get through this entirely in the next minute. So I do want to talk a little bit about the symbol that I want you to go ahead and write. In the top left corner of your paper, we're working with systems. So we'll have you go ahead and write this system, and we'll have you write, Clem, and then PLHS. Again, that goes in the top left corner. When you do that, I'm going to know that you actually watched this podcast. But again, let's go ahead and take a look at this last problem. I've just got to start part 3 to this series.